As you guys probably read in the morning mail, opening our experimental center for Astrophysics Research Center in Dark Matter, DARC, and I'm the experimental DARC director. And in honor of this occasion, we had food, and we're going to have a public lecture on dark matter. And I noticed that there are a lot more people here that come to Colloquium, so I think it's the no equations that gets everybody out. Okay, anyway, so what I'd like to do first is to introduce the people who are part of the center. Angel Garcia, you stand up. Primary force in getting this center pushed forward, so thank him for that. So you have Joel Geet, who's our theorist. Ethan Brown. World expert in purifying noble gases. Yes, got this. Cecilia Levy. First postdoc. Yes? Okay, good. Paul Stoller, where are you? Paul. And Paul Stoller is also one of the advisors we have in the center to help us get this started. And I am Heidi Newberg, for those of you who don't know me. All right, so what am I going to do? Oh. These characters in the center, they have actually nothing to do with any of the other dark characters that you've ever seen before. This is what I'm really going to do. So, first I'm going to explain why we think there's dark matter. And the answer is that dark matter, which you can't see, which is the whole point of it, it's dark, you can't see it, is inferred from the motions of the stars, which we can see. And a little demo to explain that to you. We're going to talk about what is dark matter, but we're not going to answer that in any complete way. Then I'm going to talk about experiments to directly detect dark matter, and in particular the xenon experiment. We have 2 members of xenon in the group. A little bit on the physics of dark matter, and where is the dark matter in the Milky Way. And that's where we're going to end at. Okay. So, I was charged with explaining to you why it is that we think that there's dark matter without using any equations. And like Scott Dwyer made me this wonderful demonstration where I can explain how there's like orbits, you know, of things going around. Although my demo got a little out of hand, and I was kind of afraid to do it in this space, the glass behind me and everything. So I actually made a movie. And by the end of the movie, you're going to have to pay a lot of attention because it's very short. Okay, so get your attention ready. At the end of the movie, you're going to understand why it is that we think there's dark matter. Let me see if I can get that movie up here. All right, first I have to turn the sound on. Okay.
Is a galaxy. The galaxy is an orbit around the cluster, and my gravity from my mass is the force that keeps it going in a circle. If it's going faster, I need more force to keep it in a circle. And that force comes from the dark matter in the cluster, and if there's no dark matter, it flies apart.
Okay. Covers number 1. Actually, I have a little more to say about that. That explains basically what the basic idea is if something's going around, and we have planets that go around the sun, we have stars that go around the center of the galaxy, we have galaxies that go around the centers of galaxy clusters, and what keeps them in their orbits is the mass of the thing that they're orbiting. And so you can see a relationship between how fast they're moving and how big that force is, and that force is due to the gravity.
Heidi, microphone.
Oh, sorry, I turned it off. All right. Okay, tell me how to.
Oh, turn that up.
Okay, so what I have here, not to scale, is a picture of the solar system, which seems to have stopped. And you can see in the solar system, the only thing is to scale in this is the speed that the planets are going around. And the speed of the planets that are close to the sun are going around faster. Why are they going around faster? The reason is that they have more force from the sun. Why do they have more force? Because they're closer to the sun, right? So they have to be going faster in order not to fall in. And if you actually take the speeds of the planets going around the sun and you plot them as a function of how far they are away from the sun, you see that it falls off in what we call a Keplerian decline. The planets that close to the sun have very high velocity, and far from the sun they have very low. Now, in the solar system, almost all of the mass is the sun. The planets, the comets, the asteroids, all that is practically nothing. Pretty much all the mass is in the sun. So if you have a system where all the mass is at the center, you expect to see a curve like this when you plot the velocity versus distance from the center. Okay? So we see in the solar system. We see a completely different plot when we look at a galaxy. And the galaxy that's in this inset is a famous one, the Andromeda Galaxy. And the plot shows you the speed that the stars are going around the Andromeda Galaxy as a function of how far they are from the center. And I'm going to take this picture of the Andromeda Galaxy, and I'm going to put it to scale at the bottom of the plot of how far out the stars in the Andromeda Galaxy go. And you can imagine that if you're out here at 100, if all the matter in this galaxy, if all the mass came from the stars, then out here it would pretty much be like the solar system. All the mass is at the center and you're out here, and we should be seeing that Keplerian decline. We should see the velocities going down and down and down as we go out to the edge of the galaxy, and we don't see that. And what that means is that the mass in the galaxy is not mostly in the center where the light is. It extends out very far in what we call a dark matter halo. The halo, in this case, has nothing to do with a ring around anyone's head or anything. It's more of a spherical construction. And so we kind of think of galaxies as being embedded in this much larger, more extended structure of mass. But we don't see that mass. That mass is dark. Okay, and whatever that mass is that's causing those rotation curves not to fall as you go out, that's the dark matter. Okay. And you guys, if you have questions, you can ask them as you go through. Now, I wanted to tell you a story of how dark matter was discovered. In 1933, Fritz Zwicky looked up at the coma clusters of galaxies, and he looked at the velocities of the galaxies going around the cluster, and from that he inferred the mass of the coma cluster, and he figured from those measurements that there was about 200 times more stuff in the galaxy than he can account for in the regular matter you can see in the galaxies of the coma cluster. And he was so confident of this result that he published a paper in Acta something Physica, some obscure journal in German. And somewhere in one paragraph in the middle of that paper it says there must be some kind of dark dunkel Materie, as it's in German, that is holding this cluster together. But he had to conclude at the end that because the velocities in coma are so big, there's got to be some as yet unsolved problem there. Now, Zwicky you figure having discovered there's 200 times more stuff in the Coma cluster than you could tell from the galaxies, he went out and started working on that problem right away, right?
No.
No, he did not go work on that problem. He went and worked on a lot of other problems, and very famously made the Zwicky catalog of galaxies, and so he did some really great work, worked with supernovae, worked with things. He didn't work on this. And why was that? Well, this measurement that he made was fairly uncertain. In fact, the actual ratio of dark matter to ordinary matter in the Coma cluster is more like 10. So he's off by a factor of about 20. If he'd been off by that same factor in the other direction, he would have discovered dark energy, because he would have had to have something pushing the galaxies apart. So this result was kind of unnoticed for a long time, since one, it was in German in some obscure journal that nobody read, and two, no one believed it because it wasn't a very certain result. In fact, he wrote a paper in 1937 in which he explained in a very good journal in astronomy the method that he used to calculate this, but he did not put in the result in that paper, only the method. In the late 1960s and 1970s, a number of astronomers, and most notably Vera Rubin, were looking at the rotation curves of galaxies. And so they were making the plots like the ones I showed you, of the velocity of the stars in the galaxy as a function of the distance away from the center. And by 1980, in a famous paper that was, first author was Vera Rubin, she concluded that it is inescapable that non-luminous matter exists beyond the optical galaxy, basically what we have today. And we'll see that this, on the bottom, I put the citations from the ADS abstract server as a function of year from when the paper was written. And Vera Rubin wrote her paper in 1980, got a lot of citations, got a lot of notice. When I was a graduate student in the 80s, I was told Vera Rubin discovered that there would be dark matter in galaxies. But then, I'm not sure what happened. Somebody eventually found this paper of Zwicky's, and remember Zwicky muttering something, and Zwicky is very well known for being brilliant and difficult. They found this paper back there saying that he had found dark matter from this problem earlier, and he got a lot of airtime in public talks because of this very famous picture of Zwicky, where he is, the popular story is, he's saying that all of his colleagues are spherical bastards. And you might want to know, what's a spherical bastard? It's because it's a bastard no matter what direction you look at. And so he's very popular in public talks, as you can tell. And what's shocking to me is that until Vera Rubin published her paper in 1980 and was working on it in the 70s, actually published a paper in 1970 on Andromeda, he got no citations, right? All of a sudden they said, okay, Zwicky found it, and now he's getting 60 citations a year, and she's getting 27. So as best I can tell, Vera Rubin is the woman who discovered that Zwicky discovered dark matter. But that's not what Wikipedia says. Wikipedia says that dark matter was first postulated in 1932 by Jan Oort, and it cites a web page that's put up by Ed Bertschinger at MIT. That great source. I went back and I looked at this paper. It's a great paper by Jan Oort, because what it does in this paper is he measures the mass of the disk of the Milky Way by looking at the oscillations of the stars going up and down through the disk. And he says, hey, you know what? The mass to light ratio is higher and lower in the disk than it is higher in the disk. And so it seems like there's some invisible mass in the plane. Well, yeah, probably there is. Gas, probably. But he's not getting the same kind of citation rate that Zwicky did, even though he was a year earlier. Why is that? is because, as far as we know, there's no concentration of dark matter in the plane of the Milky Way, right? It's this big halo out there. As far as we know, it's not concentrated to the plane, so it's hard for astronomers to stomach that as being the beginning of dark matter. In fact, maybe Jan needs some help. Maybe we need another young female physicist to find out that there's dark matter in the disk and discover that he discovered this in 1932. In fact, aren't you working on that, Julie? So maybe we can find out that he did discover dark matter first, but he's going to need some help. All right. I still think it was very Rubin. All right, now we're going to move on to what's the dark matter. We're going to skip forward to today, no more history. So there's a book that's actually come out this year by Katie Freese called The Cosmic Cocktail. And in The Cosmic Cocktail, she lays out the distribution of, if you were going to make a universe that was like ours, how much of each thing would you need? And you put in 3 ounces of dark matter, whatever that is. And then you put in 7 ounces of dark energy. Now I want you guys all, when you leave here, to never get confused about the difference between dark energy and dark matter. They're very different things. Dark matter is whatever it is that causes more force on the stars and the galaxies that holds galaxies and clusters together so they don't fly apart. Okay? It's a force that pulls in. Dark energy is whatever it is, and I have less idea what dark energy could be, whatever it is that is pushing the expansion of the universe apart, so that the expansion seems to be going faster and faster and faster. So it's completely the opposite thing. Okay, yes?
Is it a force or is it just a thing?
I have no idea. Look, I mean, dark energy is whatever it is that is causing the universe to go, to be expanding faster and faster. Whatever that is called dark energy. I know the guy who coined the term dark energy. It was a great newspaper story. His son got a lot of press, dark energy. And I thought when I first heard this, because he's a theorist, when I was a graduate student, I was told 99% of the universe is dark matter. Why is that? Because we could only see about 1% of it of the closure density of the universe in stars and stuff. And since theorists knew that 100% that you had to have the critical density universe, all the rest of it had to be dark matter, right? And when they found out that there was this force pulling apart and you had to modify the equations of general relativity and then you didn't need to have that density of matter anymore, this is a way they could not be wrong, or at least not off by an order of magnitude, by creating another energy term. But he actually had a better reason for it, which I discovered later. But anyway, it's whatever it is. Okay, it shows up in Einstein's equations as something that is in the mass energy tensor. That's what we call it. All right, so there's dark matter and there's dark energy, and a lot more dark energy than dark matter. All right, then you've got half an ounce of hydrogen and helium gas in the gas state, about 0.03 of an ounce of other chemical elements, 0.05 of an ounce of stars, so not too many of those, and of course planets and all other things in the solar system are much less than that. Right? For a while, people thought maybe the dark matter would be neutrinos, but nope, not enough mass there either. There's light from the beginning of the universe. That's not enough. People always want to put black holes in because they sound cool and seems like they can be pretty massive, but sorry, black holes won't do it either. And basically, people have gone through all of the things we know that have massive energy and counted up how much there could possibly be, and there's not enough. And so the rest of it, it's the mass that's holding it together, is the dark matter.
Can I ask a question?
Absolutely.
So there was this long story when I was in school about things like brown dwarfs and machos and all these other astrophysical explanations. Those seem to have kind of gone away.
Yes, they went away for 2 reasons. One reason that they went away is that people did microlensing surveys. So they looked at a place that had a lot of stars in the center of the galaxy. And they surveyed that part of the galaxy for a long time, and if a brown dwarf passes in front of the star, it lenses it, and so you get a brightening. And they did find this. They found lenses, they found brown dwarfs that went in front of stars, and they saw the characteristic peak, but they didn't find enough. The other reason that they're not popular is that if you go back to the Big Bang nucleosynthesis, and you go through all those calculations, they can't make enough normal chemical matter in the Big Bang to account for this much density of matter in the universe. And those are the two reasons people don't really like that as a solution. Okay. All right. So, at the end of this, we believe that a new type of particle, maybe a WIMP, a weakly interacting massive particle, or an axion, or a stereo-neutrino, or a wimpzilla, or some other kind of thing, is out there and causing this mass that is holding galaxies together. In fact, billions of these particles per second are passing through your body right now. Here. Okay? So I want to ask you guys, how many of you believe that there are exotic little particles, billions of them, passing through your body right now? See, we got a lot of physicists here. Because every single one of you physicists should have your hand up. Because there absolutely are little particles passing through your body right now. Okay? And these things are neutrinos. They're things we know. They're not dark matter particles. There may also be dark matter particles, but there are neutrinos definitely passing through your body right now. And these are things that we have discovered. This is a picture from a bubble chamber tracks where the neutrino comes in from the right side and decays into some other things which pass through superheated hydrogen and make a little bubble trail. This is a photograph of the trails from the bubble chamber. And you can see the products of that interaction between the hydrogen and the neutrino. They're absolutely there. This neutrino was made in an accelerator, but most of the neutrinos we have on the Earth are made in the sun. They're a normal product of the fusion of hydrogen and helium in the center of the sun. And they interact so weakly with matter that the vast majority of them pass right through the sun as if the sun wasn't there. And they go out in every direction. And by the time you get to the Earth, you've got 65 billion neutrinos per second striking every square centimeter. So you got like 1 trillion neutrinos going through you every second from the sun. Okay? So for particle physicists, coming up with some other, weakly interacting particle that's going through only billions of them every second is not such a big step. Okay? All right. Now, when I first heard of dark matter, I was in graduate school. And I really fought the idea of a crazy little particle out there that we've never heard of, making up all this mass, kind of steps in and solves all the problems that we've had up to that time. And I really wanted it to be little brown dwarfs or something, little stars that didn't make it, or Jupiters that are out there, and whatever, something that I could really hang my hat on. And I really, wanted it to be that the equations of gravity are wrong, because that was better. Who understood the equation of gravity anyway? I mean, it's just a second order solution, or whatever, but okay. But there's actually kind of a hard thing to make other theories of gravity work. And one of the reasons it's very hard to make it work is there exists something called lensing. And if you have a galaxy, so look at the center panels here. You have a galaxy or a cluster of galaxy or a star, something with mass. And if you look behind it, You see that yellow dot. The yellow dot is supposed to be a source. It could be a galaxy, it could be a quasar, something like that. Then the light from that source, as it passes near the massive object, it bends. And that's the same thing that happens in lenses, like in your glasses and stuff. They will bend the light as it goes through them. And so if you're the guy who's over here on the green Earth and looking back past that galaxy and the light that's coming from the yellow source, it doesn't appear to be coming from where that source is. It's coming from the other direction. And so if the sources are very aligned, you might see, instead of the yellow spot, you see that Einstein ring, the orange ring. Or if it's a little off kilter, you might see two orange dots on the right and one on the left, all the same object, but different images of that same object. So, you know, this has been observed, very well observed. It's predicted by general relativity, and it's very difficult to get alternative theories of matter that are consistent with this and causes rotation curves. And then the one thing that's always put up that really makes it even more difficult is the bullet cluster. And I'll show you that in a second. This is an example of a cluster of galaxies. And you see these little arcs in here. You know, we actually saw those as a graduate student. We saw little arcs like this in the images. But we always sort of ignored it because we didn't know what those could possibly be. But some smart person figured out that they were lensed galaxies from behind the cluster, right? So these are distorted images of very distant galaxies. And you can use the lensing equations to calculate how much mass there is in that cluster by how much it has bent the light from the sources that are behind it. And when you do that mass reconstruction, you might come up with a mass reconstruction that looks something like the thing on the top. Okay? So the bottom is an optical picture that shows you all the galaxies in the galaxy cluster. And the top is a reconstructed mass diagram of where the mass in that cluster is. This is the bullet cluster. And the bullet cluster, you can look on the left-hand side, you see a tight group of galaxies under the blue haze there. And on the right, under the blue haze on the right, there's another little group of galaxies. And this is apparently two clusters of galaxies that have passed through each other and on their way to merging together and making a bigger galaxy cluster. Now, in the centers of galaxy clusters, there's very hot gas. And the very hot gas is very massive. There's a lot of gas in the universe. And it emits light in the X-rays. And the X-ray gas in these clusters has been imaged in red by Sean. Now, normally the X-ray gas is in the middle of the cluster, but these two clusters, because they have passed through each other, their gas interacts, and it's hard to get gas. Galaxies can go through other galaxies because there's a lot of empty space between them, but the gas, if it's other gas, there's an interaction there. And so the gas has been left kind of in between the two galaxy clusters because it's interacted. The blue haze is a reconstruction of where the mass is. So apparently, the mass in these clusters, which is primarily, again, dark matter, has passed through each other without interacting with each other. And so now you have a case where you have dark matter that doesn't interact, at least not much, with itself. And you have to come up, if you're going to try to solve this with modifying gravity, you have to somehow figure out how your lensing is affecting where the galaxies are, but not where the gas is in the middle. Even though there's a significant amount of gas there. The mass the mass is with the galaxies, the mass is not with the gas, even though there would be a lot of baryonic matter in the gas. So it makes it really pretty difficult to make modified gravity work. Now, there is a recent counterexample to this, just to make things more interesting. There's this cluster, Abell 520, where again there's two clusters which apparently have interacted and left the red X-ray gas in the middle. And the contours show you a reconstruction of where the mass is. And in this case, there's mass not only where the galaxies are, there's also mass where the gas is. And I have no idea if that means that there's dark matter, in this case, that interacts, that maybe there's different kinds, or if there's something we don't understand about this cluster, or what the difference is between these two examples. But there are always counterexamples, so just wanted to show you that too. All right. Dark matter direct detection. Immediately in the 1980s, people started looking for weakly interacting massive particles, looking for dark matter. And they're looking for dark matter by trying to find dark matter having a very small, once-in-a-while effect on a nucleus that's in on Earth somewhere, and looking for very tiny changes. Either it moves an atom in a crystal and causes a vibration that can be felt by a very sensitive apparatus, or it causes a scintillation, so it hits a gas particle and it causes the nucleus to gain energy and give off a little bit of light, or some other interaction that's very, very small, doesn't happen very often. And we're trying to look for the effects of these dark matter particles hitting, and you want your detector to be as big as possible because there aren't very many interactions per nucleus, right? So when I was a graduate student in the 80s, there were other graduate students who were there with me contemporaneously, who were building the first dark matter detectors down in the fourth sub-basement of the Burge building in Berkeley, hoping to find evidence of a particular dark matter particle. So the search for the direct detection methods have been being built and getting bigger and bigger and bigger for 30 years. Okay, so we're very far into this. I'm going to just tell you about one of them, which is the one that Ethan and Cecilia are working on, and is arguably the premier dark matter detector of our time, the xenon dark matter experiment. This one is housed in the Grand Sasso Mountain in a tunnel that runs under it. Now, almost all of the direct detection experiments are in mines and tunnels. And why did the physicists take to the mines and tunnels? And the reason is we're trying to find very rare events. And the background for these very, very rare events is cosmic ray particles that create showers in the atmosphere, radioactive decays. If any of these kinds of particles, which again are other very small weakly interacting particles, if any of those are around, then it looks like you have a dark matter particle when you don't. And so you have to shield yourself from cosmic rays by going underground. And then the other thing you have to do is get rid of all radioactivity. You don't want any of that radioactivity in your experiment. Okay? So this is the key thing in dark matter detectors, is to get rid of radioactivity and other sources of background in your experiment. And as I said, we've got the world's expert in cleaning out the radioactivity in these detectors, so this is what we're going to be contributing here. But just to give you an idea, I actually had a banana for lunch, it's scared me a little. So the banana has 20 radioactive decays per second. And the dirtiest thing in a xenon experiment is this photosensor, which has 15 radioactive decays. The first time I read it a second. It's not per hour. So that's a factor of 5,000 times less radioactivity than a banana. And that's the dirtiest thing. So getting all the radioactivity out is a really big deal. And if this doesn't work, you guys all have really jobs in the food industry. But anyway, so that's one of the key things of dark matter experiments. All right, now how are these 30 years of dark matter experiments, how are they doing? Well, the way you usually tell how a dark matter experiment is doing is you make this plot. And on the y-axis, we have how likely is it that the dark matter will interact with the nucleus. Okay? And so, since we don't know what the dark matter particle is, there's a little bit of uncertainty in what fraction of the time it will interact with the nucleus, but that's your y-axis. And on the x-axis, we have the mass of the particle. And so these experiments, they usually, if you see the curve there, the experiment name next to the little curve says that that experiment excluded all of the region of the plot above that curve. And as time has been going on, the curves have gone down and down and down and down and down and down. The bottom one here is a xenon experiment for 2012. There's a more recent one for Blux, which is a little lower. Next year there'll be another one from xenon, a little lower. This is a constantly changing plot. But we're ruling out more and more of the possible places that these WIMPs can be. Now, that's with the exception of a few things. These blobs in red are detections, or possible detections. All right, so there have been a handful of dark matter experiments that have claimed a detection or claimed a possible detection. And there's a problem, though. There's actually, if you look at this, the area on the top right of that, or top left of the plot, there's a few of them around 10 times the mass of a proton. And so there's been a lot of, excitement that maybe there's a WIMP that's around 10 times the mass of a proton. But the later experiments have excluded that region of the diagram. So what does that mean? You have kind of two possibilities. One of them is that there's physics in dark matter particles. Because there's a lot that goes into calculating. Each detector has a different material that interacts with the WIMP. If the materials don't react as, if the comparison isn't the way we think it is, we go and square the mass of the nucleon or something. There's some other physics of the dark matter particle that makes one detector see it and another one not see it. That could be that there's physics that we don't understand that's causing this. Or it could be that there's background in these experiments that we don't understand. So far, I think most people are thinking it's background in the experiments we don't understand, but it may not be. There may be reasons why one detector is good and one not. But there are as yet no confirmed. We don't have a case where one experiment has found a dark matter particle and another one has said, yes, we see the same thing. We haven't had that happen yet. Okay? I think maybe some of these people saw what happened with Zwicky and they're just trying to say we found something in case it turns out to be true. All right. So there are two problems with the limits on the particle mass. One is they depend on the probability that a dark matter particle interacts with a detector. Okay? So that is something that you have to calculate. And I have a plot here, which Joe Deep gave me, of a paper that he wrote where he actually used lattice QCD to calculate, using all of the physics of the problem, what the interaction rate would be between a WIMP particle and a nucleon in a detector. Now this is for a particular model, which is going to use, you have to calculate for each particular model and then see how the different models compare with each other. And what he's told me is that before this, the dotted line shows you what people use as a rule of thumb. Could the interaction on the y-axis could be anywhere basically on that plot. But he was able to, for this model, come up with a really good interaction rate. So the how well we know whether we have detected dark matter or not depends a lot on theorists figuring out what the interaction rate should be for a particular kind of WIMP or a particular kind of dark matter particle that's not a WIMP. The second thing is that it depends on the local density of dark matter here at the Earth where we're detecting it. And that's the kind of research that I do. I try to figure out how the dark matter in the Milky Way Galaxy is distributed. And then in addition to that, we already know that these particles have, they can easily have their own physics. I mean, these neutrinos that came from the sun, we found out after the fact, that they can change from one kind of neutrino to another. We didn't know that before. So dark matter, we don't know what it is, it can have its own physics, and that will affect both the density in the Milky Way. We can view how particles are distributed in the Milky Way and then infer something about the particles themselves. And it also has an effect on the probability that it will be detected, so on the rate that you expect to find in your dark matter experiments. All right, now I want to spend just a couple minutes talking about where dark matter is in galaxies and why that's an issue. This is a simulation. I like this one. It's a little bit old, but I like it because it shows the universe expanding. So you start with a little piece of the universe early in the universe, and you see this is the dark matter, and the universe is expanding. But as the universe expands, the little pieces of dark matter come back together. They gravitationally collapse. They come back from gravity, and they form little, we call them subhalos. And those subhalos, orbit around the center of whatever the closest mass is, and they merge with each other, and they break apart, and they form bigger and bigger structures as the universe goes on. And galaxies form through this kind of merging process where dark matter and stars and everything else come together and make these big, lumpy messes. And so at the end of these simulations, they end up with galaxies that have a lot of little galaxies around them, like thousands. Okay, that's fine. You can have a galaxy, a big galaxy like the Milky Way, can have thousands of little galaxies around it. Here's a more, a higher resolution simulation. At the end of the simulation, a galaxy with thousands of little dark matter blobs all around it. But the thing is that when we look at a galaxy like the Milky Way, we don't see thousands of dwarf galaxies out there. So if it's true that it's lumpy like this, if the Milky Way is lumpy like this, then all of those little lumps don't have stars in them. They're just dark matter lumps. Is that true or not? I have no idea. I always wanted to find one of these. Oh, I found a dark matter lump. But so no one yet has determined whether they are there or they're not there. And that's going to affect the rate you see. In fact, and here's a case where it kind of is here. This person, this is recent. Somebody said, oh, I know how to make all those lumps in the go away. I'm going to have, in the early universe, the dark matter have a little bit of interaction with light, and that'll smooth it all out in the early universe, and we'll get rid of all the lumps. Okay, that's one way maybe we could do it. Maybe not the right way, but it shows you the idea that the physics of these dark matter particles can affect the outcomes of the simulations that are running them. So there's an interplay between understanding the physics of these particles, understanding how they are distributed in galaxies, and understanding what we're going to detect in the direct detection experiments. You might be surprised how little we know about where the dark matter is in the Milky Way. We think that it's in some big dark matter halo, but we have no idea if it's spherical, if it's squashed towards the disk, if it's prolate like a football, if it's triaxial, lumpy. We have no idea. You'll find papers that claim all of these things. So how do I work on this problem? I look at actually dwarf galaxies. And the dwarf galaxies that fall into the Milky Way have their stars pulled off of them by tidal forces. They're pulled harder on one side than on the other side, and if they're pulled hard enough, the stars come off, and then they go into orbit around the Milky Way, either ahead or behind, leading or trailing the dwarf galaxy. Now, what's special about those stars is they are the only stars in the Milky Way for which we can know not only where they are and what velocity they're moving, but also where they were in the past. And knowing where they were in the past is a key part of being able to use them to understand the gravitational potential, the field that they have gone through. And so these, if you can figure out which stars belong to which dwarf galaxy, which has been an issue, these can be used to backtrack and figure out where what the shape of the dark matter distribution in the Milky Way is. You can also use it to find out how many lumps there are, because you'll have different effects of it going through a lumpy halo than not a lumpy halo. And we're currently using a Milky Way Home to simulate. We run simulations of dwarf galaxies like on the lower left, going around the Milky Way and breaking up into these star streams in different shape dark matter halos, and compare them to the distributions and velocities of stars we see in the sky. Okay? And then if we can make all of those match, then we can figure out which of the distributions of dark matter is correct. And to do this, we use a volunteer computing system called Milky Way Home. At any given time, 25,000 people all over the world have computers that are crunching through our data. We have a server here, sends out work units to all these people, they crunch through some of the calculations, send the results back to us. So we have a half a petaflop supercomputer that goes just for this Milky Way problem. Okay. So I'm going to end with just telling you this. I haven't covered everything there is to know about dark matter. But this is a really good time to be working on dark matter. And if you talk to anybody who is an expert in this field, you know, like I said, this is 30 years. People have been working on this for 30 years. And they're starting to find detections. Not only possible detections in direct detection experiments, but also possible detection in something I didn't talk about called indirect detection experiments, where they're looking for if you have two dark matter particles and they annihilate each other and they produce positrons or neutrinos or photons or gamma rays, something like that, you might be able to detect those things coming from wherever the most dense dark matter parts of the galaxy are. And people are starting to see hints that maybe they do see those things. Maybe they don't, but maybe they do. And I think that people in the field really feel like finding what dark matter is something that we can imagine doing in the next 10 years. So in the foreseeable future. So it's a really good time to be working together and try to make that happen. And I'm done. Are there any questions? Yes.
So if dark matter only interacts gravitationally, why does it cluster at all?
Gravity will pull things in.
Yeah, but then they just pass through each other.
No, it freezes out of the expansion of the universe. These simulations where you see them going around and creating larger and larger structure formation, those are just n-body models in an expansion.
Only gravity in those
It's
models.
just gravity. Yeah.
Is it always regular gravity? Like, does it always follow the gravity also we have?
Yeah,
where do you guys find the gravity?
I'm not aware of any cosmological simulations that use any of the theories that try to modify gravity. I mean, all of these use the textbook gravity. Yeah.
How do you differentiate between a neutrino event and a dark matter event in your calculation?
I'm going to give this to you.
So, well, in general, I can generalize that question to distinguish between a dark matter event and any kind of other event. And we do that in several ways. First of all, with calibrations, we understand how different types of particles will interact in our detector. And a neutrino will predominantly scatter off of the electrons, whereas dark matter will predominantly scatter off of the nucleus, and that will give a different characteristic signature. But we also, beyond that, we look at all different sources of backgrounds, and we can quantify how many neutrinos are coming from reactors, how many are coming from the sun. We have expectations for how many neutrino interactions we expect in our experiment, and the same for all different types of backgrounds. And so the typical particle physics way of dealing with this is to understand all of your backgrounds extremely well and look for any excess of this as a source of new physics, in this case dark matter.
Yes.
I didn't quite understand one part. It sounds like we understand the effect and like the force that dark matter is having, but if we don't know the distribution, how do we know about how much it is or is like the range of like distance that would be apart from each other just a small factor, and it's not going to make much of a difference how much mass there is.
So I described 2 ways we know how much dark matter there is. Well, actually 3. One way is to look at the velocities of galaxies in large clusters. Okay. One way is to look at the gas, mostly the gas, because you can't see stars very far out in the disks of galaxies, to see how quickly they're rotating about the center of the galaxy. And the third way is through lensing experiments to see how much the light bends. And those experiments are only sensitive to the very large scale picture of how much mass they are. They don't give you a high resolution picture of where the mass is. I mean, if you're looking at disks of galaxy, you're only getting the what's in the disk. If you're looking at halo stars, usually you're having to do it statistically. We don't have ways to get the resolution on where that dark matter is from those simple experiments. And that's why I think that looking at tidal streams, because then you can have a more sensitive measure of where those actual stars went through the galaxy and see what they've experienced in that path is the important thing that we're trying to add.
So they don't depend on where they're located at, the first 3 methods you talked about?
It matters how they're distributed radially, but it's not a very sensitive discriminator of the overall shape. Yeah.
But when you showed your little 2003 simulation of the early universe and the expansion and how dark matter kind of appears in it, is there a reason why that's not very spherically symmetric? It appeared like the bottom rim had like a higher intensity in the earlier time than the top rim. Is that like a simulation thing, or is that something you know about dark matter in terms of how it's dispersed itself?
So I would have to go back and rerun that to see if I can find what you're saying. But I think that was actually a fairly small section of the universe that created one kind of big structure. And so it may have been not a large enough scale for it to average out.
Okay.
Is there any difference in terms of the amount of dark matter that's associated with different galaxies, or is there any reason to think that it isn't necessarily associated with galaxies?
As far as, we've always found that large galaxies always have a lot of dark matter, have a large amount of dark matter, and clusters always have an even larger amount of dark matter. There's more question about the smaller galaxies, because there's the dwarf galaxies, for example, that are in orbit around the Milky Way, are thought to have a very high fraction of dark matter. But that's, I think, that measurement is sometimes makes them, there are 2 things. One is they make an assumption about the cluster being in an equilibrium state. And the second thing is that there are very few stars in those dwarf galaxies that are bright enough that they can use them to make those measurements. And so there's some trouble with getting those velocities exactly right. So where we're less sure about it in galaxies is on the very dimmer galaxies. But what people tend to believe is that the smallest galaxies have the highest fraction of dark matter.
Does light bend around dark matter?
Yes. Yeah.
This may be very naive because this is not my field at all, but is there any reason to think that without matter in the universe at all, space would be flat? So what I'm getting at is, what if space in general was wavy over a very, very long distance, and all of these concentrations of matter, or what seems to be concentrations of matter, could just be explained by the standard space being, I guess, space-time being wavy, kind of like a sheet of lasagna. That's a terrible thing to say. But has anybody ever considered that?
So I'm not exactly sure what that particular shape of space solves, because what you're seeing is where you have concentrations of what I call baryonic matter, normal matter, that you have a displacement between where the mass is and where the baryonic matter is. That's somewhat spherically symmetric. And I'm not sure how a wave causes that to happen. I guess that's what I'm having trouble understanding that as the solution.
Well,
When I said wave, sorry.
yeah, I mean, if you have a wave in the metric
Yeah,
space
that's what I was saying, yeah.
and if you believe Einstein's equation, there's a mass energy distribution that's causing that, because you have an equation of motion relating the geometry to the mass energy distribution. So you can't escape, if you believe Einstein, you can't escape. There's something there.
Yeah, the other thing is that the first thing you had is that there's no mass and it's flat. There's also no dark energy either. They both have. Yeah.
On your graph for the image where you had the cross-sectional versus the max, you had that lower limit. It looked like there was like a gray region in the bottom right part of the screen. There wasn't anything like that pointing like that. I was looking to.
So that's basically the region that's favored by most supersymmetric models for where we expect dark matter to be. So a lot of theories aim to that region as the focus center of where we could most likely discover dark matter. This one, the lower right here.
Yeah, but I can tell you, I've been watching these for a long time. That region is creeping down.
And there's a reason for that.
So it reason.
Yeah, no, there's a reason for that. That's because the theories take in constraints from experiments. So both the direct detection experiments that move it downward and the collider experiments that move it to the right, because it's based on not seeing supersymmetric particles in the LHC, that pushes these to higher mass as well.
Okay. Are there other questions?
I have a question. So the bullet cluster, picture is fairly recent. It's not that old. And this one that you showed of another
That's
cluster
very
is
recent.
very recent. So I'm just kind of curious about what's happening in terms of observations, satellites, and things like that, and trying to understand dark matter better.
You mean for that particular case?
Or just in general, like, are there new satellites going up that's going to answer more of our questions, or, is there more surveys that are being done that are going to give us more than SDSS, or?
There are definitely more of all of those things. I think that the satellites, so the direct detection experiments sort of take to the lines and tunnels, right? The indirect detection experiments go to space and the South Pole. They're always going to extreme environments. I am not really keep track of the NASA, what missions are planned and funded and which things are going out. But we definitely have satellites that are up now that are doing indirect detection experiments where they're trying to look at galaxy center and dwarf galaxies and places where you expect to find a lot of dark matter to try to find products of wind annihilations. And we have a lot more surveys that are, so this whole space telescope in Chandra are being used to look at things like these clusters to see where the mass is and where yes, all of this is going on. Some of the things that went up as new are just parts of long-term, surveys of cores of galaxy clusters and gassy clusters and all of that. I mean, this is, I think, a lot of, as you know, a lot of concentration in the particle world is going towards dark matter because people think it can be solved, right? So it's one of the big questions in astrophysics, and it looks like it could be solved in the next decade.
Is it always found in the dark matter? Or just right there?
Well, if there's no normal matter there, it's hard for us to know it's there.
Yeah, but let's say something's traveling through space and just randomly takes a turn. Looks like it randomly takes a turn.
Well, there have been claims of people seeing things that maybe could be due to a lump of dark matter. They haven't been confirmed. There were a number of years ago observational claims that there might be something that looks like there's a lump going through it. I would love to definitively find such a thing, but as of yet, I don't think we have a definitive case of just finding dark matter. Yeah.
Do you think dark matter can form dark black holes or blacker black holes?
There are such things as dark stars that have been theorized in the early universe, where you make a very massive star with dark matter in the center, which completely changes the physics of things there. I would assume there that you could have dark black holes, but who would care what's in the black hole, right? Go on. Yeah.
What does a dark star radiate?
What does a dark star? Now you're way off. We're gonna have to get a dark star expert to come in here and talk. This is there's nothing that exists in the universe today. Okay, so nothing has been observed. Yeah.
So what's the next step in your research if we ever detect dark matter and you know this stuff is not?
What's the physics of it? How did it get here? I mean, that's all, that's at least a generation. We find the dark matter, we're going to have to know what does it do. Are there any others? Was there going to be one dark matter particle? That would be unusual. All right. Yeah.
End with a practical question. Have you and the others that are involved in the DARC program taken the precaution of taking some really wacky photographs so that future generations will be able to tell stories like Dr. Zwicky? And if not, why not?
Your friends want to know.
All right. I think we'll let people leave. If people have other questions, they want to